Hi, and welcome to Physics Accelerated Motion Problems. These are kind of hard. We did the easy ones in class with the regular acceleration, but now there's other equations. So what I've done is I put the other equations here on the board, and you need to put them on your equation sheet. And you probably need to make a chart where you have the symbols and what they stand for. So all the A's, if there's an A in the equation, it stands for acceleration, and it's going to be measured in meters per second squared. All of the V's, whether they're V final or V initial, those are the speeds or the velocities, and they're going to be measured in meters per second. Sometimes they'll be positive, sometimes they'll be negative, depending on the direction. The same thing with the acceleration. The displacement is x. So all the x's they'll either say distance or displacement, and those are going to be measured in meters usually, sometimes kilometers, but usually meters. T stands for time, and that's going to be measuring in seconds. It'll be measured in seconds most of the time. So you have A's and V's and delta X's or X's and T's, and you need to know when you read the word problem what you're dealing with so that you can choose the correct equation, because now there's a lot more equations. So I'm going to read a problem, and then we'll do one from the worksheet that hopefully you have already in your possession, or it's online and you can download it. But we're going to do a couple together before we do the one on the worksheet. The first one, if you can access your book, if not, it's okay. It's on page 69 in your book, number 18. It says, if a car accelerates from rest at a constant rate to 5.5 meters per second squared north, how long will it take the car to reach a velocity of 28 meters per second north? So that's the entire word problem, and there's a lot to it, but you can break it down from the clues that they've given you. So anytime that it says that something is starting from rest, when you see those two words, that means that the initial velocity is 0. There are clues, and from rest means the initial velocity is 0, and initial velocity is v, and it has an I as a subscript to show you it's the initial, it's where we're starting. The next part of this problem says that it's accelerating at a constant rate of 5.5 meters per second squared. As soon as you see that squared, that means that that's the acceleration. Acceleration is the rate at which the speed changes. So this is going to be 5.5 meters per second squared. You need to write all of this down so that you know which equation to choose. So we've got 5.5 meters per second squared, and it says, how long does it take? How long does it take is asking you for time. How far it goes is distance. How long does it take is going to be a time thing. So we're looking for the time. For the car to reach a velocity of 28 meters per second. So it's starting from rest, and it's reaching a velocity of 28 meters per second. So that's going to be the final velocity. You need to write down all of this information from the problem. If you don't do this, I take points off. I did it on the last test. I'm going to do it on this test. And the reason is, look at all those equations. And sometimes you can use more than one equation and you'll still get the same answer. But if you list everything and look at what you've been given and what you're trying to find, then you'll know which one to choose. So this one has an initial velocity and an acceleration and a final velocity, and we're looking for the time. There's no delta x in this. There's no distance in this, and they're not asking for a distance. So we're not going to choose any of the equations, these last three, that have delta x's in them. And so we want to pick the easiest equation to manipulate or change to solve for the time. I think that's probably the first equation. The first equation says that the acceleration is equal to the final velocity minus the initial velocity divided by the time. We have the acceleration, it's right here, 5.5 meters per second squared. We have the final velocity, it's 28 meters per second. We know the initial velocity, it's 0, so I'm just going to cancel that out altogether, and we're looking for the time. When we rearrange this equation, I multiply both sides by the time, and then I divide by the acceleration. It's just simple algebra. So I'm going to take the final velocity, 28 meters per second, and I'm going to divide it by the acceleration, 5.5 meters per second squared. And that's going to tell me how long it took for the car to accelerate. So I take 28 divided by 5.5, and I get 5.1, and that's going to be seconds because time is measured in seconds. It's really important that you list the information, and then that will help you choose the correct equation. You could have used the second equation as well, but it was just, I think, easier using the first equation, but maybe not. It doesn't matter. You would get the same answer because the second equation comes from the first equation. So this is how you're going to do all of the problems. Let's do another one together. If you have a book that you can follow along, if not, that's okay. I will read the problem. A race car travels on a straight racetrack with a forward velocity of 44 meters per second and slows at a constant rate of velocity to a velocity of 22 meters per second over 11 seconds. How far does it move during this time? So once again, a race car travels on a straight racetrack with a forward velocity of 44 meters per second. That's the initial velocity. That's what the race car is starting at. So the initial velocity in this one is 44 meters per second. It's very fast. It's a race car. And it's slowing at a constant rate to a velocity of 22 meters per second. So they have that expression in there, it's going to this velocity. That means that's the final velocity for our particular problem. And it's slowing down, so it should be a smaller number, and it is. And it says it's doing this over 11 seconds, so that's the time. And they want to know how far does it travel during this amount of time. So this is the initial velocity of the race car. This is the final velocity of the race car for this particular amount of time, and it's taking 11 seconds to do that. And they want to know how far has it gone. So we have VI, we have VF, we have T, and we're looking for X. This one has X in it. Well, you can't use the first two equations then because they don't have an X in it. Here's one, it's solved for X, it has a VI, it has a VF, and it has a time. That's perfect, and it's already solved for delta X, so all we have to do is plug the numbers in and do the math. So we write down the initial equation that we're planning on using. We always do that. And then we just put the numbers in because it's already solved for the displacement. So this is going to be 1/2. You have to do what's in parentheses first. So 44 meters per second plus 22 meters per second. And then you multiply by the time, which is 11 seconds. So do what's in parentheses first, 66 times 1/2 times 11 is 363. But for significant digits, it'd be 360. When you add these two together, you're going to have meters per second, and then multiply by seconds. The seconds are going to cancel out, leaving you with meters, which is what a displacement should be measured in. So that one wasn't too bad, as long as you list the information from the problem first, because these are going to be all mixed up on your practice sheet. We're going to do one more from the book, and then we'll set one up for you on your worksheet. So I'm trying to find one. That's not it. Okie dokie. This one says, I don't want to do that one either. I need to stop this probably at this point. We'll do the one from the worksheet. On your worksheet, if you've downloaded it, number 1. Now let's do number 4. Let's do number 4 together. I'll set that one up for you because it's going to be a different equation. Number 4 under the accelerated motion worksheet, it's on Schoology. It says a sailboat starts from rest and accelerates at a rate of 0.21 meters per second squared over a distance of 280 meters. They have two things that they want you to find in this problem. They want you to find the final velocity, and they want you to find the time it takes for the boat to travel. So we're just going to set this one up, and I'll tell you which equation to use, and then you try to work through the math and do part B on your own. So the sailboat is starting from rest. If it goes to a stop, the final velocity is 0. If it starts from rest, then the initial velocity is 0. And it says it's accelerating at a rate of 0.21 meters per second squared. As soon as you see the meters per second squared, you know that that's an acceleration. The square on the second tells you that. And it's going through a distance of 280 meters when it does this. In the first part, they want you to figure out the final velocity. So that's VF. You don't have time for this one. That's why I particularly wanted to do a problem like this. Because when there's no time, you could use another equation and find the time and then plug it into a second equation, but you don't have to. Because the last equation of the 5 equations that we have, there's no time involved. So we can take that equation, VF squared equals VI squared plus 2 times the acceleration times the change in displacement. Because this started from rest, this entire thing is going to cancel out because anything squared is 0. This is solved for the velocity, the final velocity squared. So in order to get your right answer, you just take the square root of 2 times the acceleration times delta x. So if you take this information and plug it in here, that should give you the final velocity. To do part B, then they want you to find the time. You should be able to pick an equation now with all this information that you have and be able to find the time. We're going to do a Zoom meeting on Friday of this week for anybody that has difficulty. So that'll be the 23rd, probably at 10 o'clock, but we might set up more than one for those of you that are in calculus that might need help. So that's it for accelerated motion.